Assalamu alaikum, everybody. My name is Ahil Yaman. I do one dietitian. So now I'm going to be talking about the assignment submission that I did for algorithms for CSE 4403. So my assignment title is mainly Smart Grid. I'm like urban power distribution. So this is an integrated real-time algorithm engine for fault-free, loop-free rerouting and battery optimization, as written in the title. This is actually a real-world engineering problem. Like how a modern city can keep its electricity flowing reliably, even when parts of the power network fail. I will cover this in two parts. So firstly, I will be talking about the problem itself and then the solution, mainly what kinds of algorithm were used and why I used them. So as you can see here, I have written about the problem statement. So modern cities draw electricity from solar panels, wind turbines, and conventional plants buffered by distributed battery banks. Reliable delivery is threatened by four interlocking failure methods. So the first of them is an unpredictable energy supply. So as we know that solar panels are used widely in many areas. So they are mainly um, relying on energy produced by the sun. So they stop working when the clouds cover the sun, and wind turbines, as we know, depend on the flow of wind, and hence when the wind is calm, they also slow down. And these usually happen at times when the supply is high in demand, like when, you know, during the evening when people turn on their televisions to relax, or when people come home from work. So at that time, the demand is high, but supply is in loss. The second one is physical line failures. So we know that a storm, an accident, or a lightning strike can snap a high voltage transmission line. And when that happens, every neighborhood of that line instantly uses power. So this will require rerouting. This also introduces a third challenge for us, which is when we are rerouting the electricity, we need to make sure that we do not reroute through a line which already has sufficient load. Because when the load is extremely high, it can be that the wire can overheat, melt, or trip a breaker, and it can also cause damage like destroy the costly transformers. And finally, the fourth challenge is battery mismanagement. Batteries need to be charged when solar power is cheap and plentiful, and discharged when the main grid is under stress. If they are discharged or charged at a wrong time, there may be no backup power left, and especially when an emergency happens. So these are the problems associated with the smart grid. So now I'm going to talk about a solution approach, which is described in the next slide. The solution approach has mainly five algorithms that are uh, associated with it. So the approach is to build a single real-time algorithmic engine that chains five classical algorithms into one continuous pipeline. The key idea is that each stage's output feeds into the next stage's input, so that it can be a whole coordinated process and not five separate ones. So the first stage is the first search, which handles fault detection. The second one is minimum spanning tree, which handles topological repair. The third one is max flow analysis for capacity check. The fourth is Dijkstra's and Floyd Warshall's algorithm for optimal routing, and the fifth is dynamic programming for that with scheduling. In this slide, as we can see, I have talked about the fault detection and topology with their steps one to three, as described here. The first three stages are about localizing the fault, rebuilding a safe network shape, and confirming that the shape can actually carry the load. The first step is with first search. The input is the beat graph, and also the fault vector, which is the list of lines that just spoke as input. The algorithm simply traverses outward from every power source, and any node that the traversal cannot reach is flagged as disconnected. As you know, its breadth first search has a complexity of V plus E, which is fast enough. The second one is the minimum spanning tree, so that we can rebuild a loop-free shape around the damaged area, and so that it is as less expensive as possible, which is the minimum spanning tree obviously next year. The tree that it will form will be of the least cost as possible. So the surviving and candidate backup edges will be our input, and the Kruskal or Prim's algorithm will pick the minimum resistance edges that connects all the nodes with no cycle. This has a complexity of E log V, which guarantees zero closed current loops. The third is the max flow analysis. This confirms that the rebuilt tree can safely carry the rerouted load. The input is the candidate tree edges with maximum current capacity limits. The Edmond Cart algorithm will compute the achievable flow source to demand flow source demand flagging edges over the limit. The complexity is E square, which means it runs once per fault event and not continuously. Now the steps 4 and 5 describe how we reroute optimally and the battery scheduling as well. So the step 4 is Dijkstra's and Floyd Marshall's algorithm. Their goal is to route power from sources to substations along the least resistance paths and to be able to answer any source to destination query instantly. The input is obviously the weighted grid graph, where each edge weight represents line resistance. Dijkstra computes single source shortest paths for live routing, while Floyd Marshall pre-computes all pairs shortest paths offline, so that during an actual fault, any routing query returns instantly. Dijkstra runs in O of E log E for live queries, and Floyd Marshall runs in OVQ. But since it's pre-computed ahead of time, it only takes O of 1 to look up that value. Now, step 5 is dynamic program, which role is to mainly schedule battery charging and discharging to cut cost while guaranteeing emergency reserve. The input is the 24-hour price demand forecast. So battery capacity and charge discharge rate limits are also inputted. So the algorithm works over discretized time and charge level states to find the minimum cost charging policy. This is essentially analogous to a bounded map set problem. It runs in O of T times C, where T is the number of time slots and C is the number of charge levels, and it needs to be solved only once per plan reset. So these the 5 stages together form a closed loop control system which detects repairs, verifies routes, and optimizes the grid conditions in real time. So that was basically my presentation. Um, Basically, I used a smart grid problem that required handling unpredictable supply, physical line failures, overload risk, and battery mismanagement, all in real time. The solution addresses this with the five-stage algorithm pipeline, DFS, minimum spanning tree, max flow, uh, Dijkstra and Floyd Warshall together, and dynamic programming. So this works together as an integrated engines to, work on the problem. So that is it from my side. Thank you for watching the video. Assalamu alaikum.